Next example is a little more complicated. Here they're asking us not just for the area inside some one petal or one graph, but they're asking us for the area inside r equals 3 sine theta and outside r equals 2 minus sine theta. So we have to get these graphed. R equals sine theta, that's a real easy one. We have a circle of radius 3 above the x-axis and with y-axis symmetry. And then when we graph this 2 minus sine theta, we're going to have a cardioid that doesn't quite touch the origin. It's going to be a minimum at 1. We're going to have a maximum r at 3, 2, 3. Here and here. Since it's minus sine theta, we're going to be below, the largest part of this graph is going to be below the x-axis. So we have a graph that looks kind of like that. Alright, so we want the area inside the circle but outside our shape here. Right, so we want that area there. Right, so we need to find out the angular measurement of that intersection point there. Right, so we need to set these equal to each other. So let's see, we get 4 sine theta equals 2, so sine theta equals 1/2. So the angular measurement whose sine is 1/2. It's going to be pi over 6. Right, and then of course this is, so here we have pi over 6. This measurement is pi over 2. So I am just going to integrate from pi over 6 to pi over 2. That's going to give me that area there, and then I can double it to find the answer to this question. Right, so I have 1/2 the integral from pi over 6 to pi over 2. I'm going to do r squared minus r squared. So the outside shape here is 3 sine theta minus the inside boundary here, the inside shape here, 2 minus sine theta. Square that. E theta. Alright, so there's the setup. That only tells me that right half, so I have to double that. And if we work through that integration, again, there's some double angle formulas. We get some sine squareds in there, so we're going to have to use a double angle formula in there. And our total area, we're going to get 3√3. Last example, they ask us for the common interior of these two shapes. So again, we have to draw the shape. So we have 3 cosine theta as a circle with radius 3. Here we have 1 plus cosine theta, so that's going to give us a shape like that. So when we're looking at these, we have to be really careful here. I'm going to zoom in a little bit. Hopefully my shape will work well enough that we can use this. So the common area is this area right here. Right? Well, it's both of these. here. Right, and I'm going to find just this top part. Now, if I integrate from 0 to where these intersect, I'm going to get almost the whole shape. That's a little off, as you can see, but there's this little crescent right here that I'm not going to get when I integrate from 0 to the intersection here. There's a little crescent of this circle that's not going to be included in that. So when I find that those intersect, these intersect when 3 cosine theta equals 1 plus cosine theta. So 2 cosine theta equals 1. So when the cosine is 1/2, that's going to be pi over 3. So if I integrate from 0 to pi over 3, this is just the area that's inside this inner shape. So I'm going to do integrate 1 plus cosine squared d theta. Right. But to include this little crescent here, I have to integrate from pi over 3 to where the circle meets the origin, and that is pi over 2. And there I'm integrating, I just want to find the area that's inside this circle. So I have 1 plus cosine theta squared d theta. All right, now keep in mind, this expression here is just going to give me the top half of this common interior. So when I find that value, I have to multiply that by 2 to find both the bottom half and the top half. When I work through that, that area is going to come out to 5 pi over 4 as a total.